I've been waiting to do this topic for a while now. The reason is because this topic ties together what we've just finished, centripetal force, along with some stuff that we did in Unit 2. I'm going to ask you a question in a few minutes. If you know the answer to that question, and you should if you think about it, then that means you've really learned something this year. You're not just repeating what I'm saying, but rather you're internalizing what I'm saying, and you're learning to think. Okay, we'll see what that question is in just a couple moments here. Today we're going to study vertical circular motion. What do we mean by that? Well, up until now, we've talked about a car going around a turn on a horizontal road. We've talked about swinging the keys around my head on the horizontal axis. In 24 days, you're going to go on your field trip, and you're going to go on the Mindbender roller coaster, and you're going to go around 3 vertical loops. You're going to go around 3 vertical circles. It's going to look like this. There's going to be 3 times, 2 of them in fact are together right after another. There's going to be 3 times when you are literally, completely, 100% upside down in a roller coaster car going at about 100 kilometers per hour. We need to be able to analyze those situations when you're going upside down in a loop. We need to be able to analyze vertical, as opposed to horizontal, vertical circular motion problems. Well, there's 2 extremes, and we're going to take a look at those 2 extremes. The first one is when you're at the top of the loop. The second one is when you're at the bottom of the loop. Now, you could be in between, and we could analyze that. It's a little bit harder to analyze it when you're in between. The good news is we don't really need to analyze it when we're in between, because the extremes, if we've got a minimum force, minimum speed, maximum force, maximum speed, it's going to occur, all of that stuff's going to occur when we're at our extremes at the top and the bottom. Now, we're going to draw a free body diagram for each of these situations. Can you tell me, when you're at the top of the circle, upside down, in a roller coaster, or even when I'm swinging my keys upside down above my head like this, can you tell me what force or forces act on this roller coaster car? What's one of them, Michael? Let's not talk about that yet, okay? Fundamental forces, I should have said. What's one or more fundamental force that acts on this roller coaster car? Jonathan, what's one? Gravity. Gravity acts down. Hey, it doesn't matter whether you're at the top of the circle or the bottom of the circle for gravity, right? Gravity is going to act down. Okay, good, good. Let's make this one a little bit smaller, actually. All right, what else? Or is there anything else? Yep. I'm sorry? Kinetic? No, kinetic is a form of energy. Okay, so it's got kinetic energy. It's moving. You better hope it's moving anyways. Otherwise, you're not going to do a very good job at staying in the loop, right? But that's energy, not force. Any other forces here, Nick? The normal force. Okay, when you're at the top of the circle, which way does the normal force act? Yeah, the track is pushing you down when you're at the top of the circle. What about when you're at the bottom of the circle, Merrick? Yeah, normal force is pushing up on you. Now, notice I've drawn the normal force a little bit longer than gravity at the bottom. How do we know that it should be a bigger value than gravity? Let me rephrase that question. Ask it in a different way. How do we know that gravity can't be bigger than the normal force? Yeah, if you have an upward acceleration. When you're at the bottom of the circle, Hugh, you're accelerating toward the center. Well, then the upward force must be bigger than the downward force, right? Just like with elevators, when you accelerated upward, the upward force had to be bigger than the downward force. All right. Here's a question I've been waiting to ask you for a couple weeks now. What next? What's next? Jotham, what's next? Why do you do that? Dom, is that what you were going to say? No? Dom, why am I going to say, or Jotham, why am I going to say F net is equal to the sum of the forces? Yeah, look, every time you have a free body diagram with more than one force, that's what we do. That's what we did in our last unit. Just because we've switched units doesn't mean we switch ideas. If we have a diagram with more than one force acting, we say the net force is the sum of the forces. This is not new. The context is new. You know what? We did lots of different contexts last unit. Elevator problems. We did inclined plane problems. We did pulley problems, right? Down here would be the same, by the way, because it's the same two forces. Hey, what was next? This doesn't require a whole lot of thought for this one. Just remember, what was next? We replaced Fnet with something. Boy, it hasn't been that long, has it? Andrew, what's next? Fnet is also equal to what? Yeah, it's MA. But you know what we're going to do this time? Instead of calling it MA, we're going to call it M times centripetal A, or M times V squared over R. In other words, the net force is the centripetal force. We said centripetal force is not fundamental. It's got to be caused by something. Well, in this case, it's caused by two things, gravity and the normal force combined. So now it looks a little bit different than last unit, but not much. mv squared over r is equal to fn plus fg. Same thing down here. Notice I haven't plugged in any positives or negatives yet. Why not? Remember in the last unit, we waited to plug in negatives until we put in numbers. There's no numbers here yet. Okay, let's wait till we put in numbers to identify whether it's positive or negative. When we do put in numbers, Fn here will be what? Positive or negative? Get this one? Alice? Why would it be positive? Okay, because gravity is negative. Okay, fair enough. Anybody else? Fn positive, Fn negative? Dom? It would be whatever I put gravity as. So if I put gravity as negative, Fn will be negative. How come? Good, because it acts in the same direction. There's our answer right there, okay? We're going to make Fn always, Dom, in these problems negative, although technically you could make it positive if gravity was. We're just going to avoid that altogether in these questions. Just make it negative if it's down. What about gravity? That's the easy one, right? Gravity negative or positive? Oh, you better know this one. Ali, is gravity negative or positive? Good. It's acting downwards, right? Let's take a look at gravity down here, negative or positive? Negative, because it's acting downwards. What about the normal force down here? Sophie, what about the normal force down here at the bottom? Which way does it act? Positive, because it's upwards. Good. Opposite to gravity, right? What about, hey, let's get a nice fancy purple color here. What about mv squared over r once I start plugging numbers in? The top of the circle, mv squared over r, the centripetal force will be y positive. Okay, because it's an absolute value. Okay, anybody say negative? It is negative. Okay, it is negative. Now, you made a really good point there, Michael. Absolute value should be positive, right? When we solve for mv squared over r, we get a positive value, always. But there's no reason why we can't, if it's a downward force, arbitrarily stick a negative in there. Okay, and that's what we're going to do here. Okay, you're at the top of the circle. Centripetal force acts toward the center. Where is the center of the circle relative to you when you're at the top? Below you, right? So we're going to make this a negative value. What about the bottom of the circle? This one's even tougher. That was hard enough. At the bottom of the circle, which way does the centripetal force act? Hugh? Yeah. Yeah, how do you know that it acts up, Hugh? Well, the normal force counters gravity, right? So it's positive. How do you know the net force or the centripetal force is positive? Good. Yeah, think about that. If you're going in a circle, the net force has to be toward the center of the circle. If you're at the bottom of the circle and you want to keep going in the circle, then the net force has to be toward the center, which is upwards. So don't worry about those negatives until we plug in numbers, but as soon as we start plugging in numbers, that's when we got to account for those. All right? Let's do a problem. So it's a bucket of water with a mass of 1.5 kilograms is spun in a vertical circle on a rope. The radius of the circle is 0.75 meters, and the speed of the bucket is 3 meters per second. What's the tension on the rope in position C as shown below? Why would they give us a question that's so impractical like that? You can't swing a bucket of water upside down, can you? If it's got a cover on it, you could, right? Can you swing a bucket of water upside down without a cover? Can you? We got a bucket here at the bottom. This bucket experiences a force of gravity acting down. This bucket experiences a normal force acting up. Why did I draw the normal force bigger than the force of gravity on it? It has to be bigger, but how do you know that? If gravity is bigger, if the downward force is bigger, then what happens here? Then there's no net force toward the center of the circle, right? It's not going to go in a circle anymore. What's going to happen is it's going to go out like this. Water's probably going to spill. Okay, the upward force, whatever force is toward the center of the circle, has to be bigger than the force that opposes it. You have to have a net force toward the center of the circle. Otherwise, it's not called a centripetal force. All right, F net is equal to the sum of the forces. That's going to be Fn plus Fg. The net force is, well, normally it's Ma. It still is. Well, we're going to call that mv squared over r now. M is 1.5. V is 3. Don't forget to square that. R is 0.75. Fn is what we're solving. Wait a second. Fn, we're looking for the tension. I'm solving for the normal force. How do you get tension? Isn't it the same thing? I called it Fn. Could I have called it Ft? Force of tension of the rope? Sure. Okay, you want to call it Ft? Go ahead. I like to just keep calling it Fn just to be consistent from one problem to the other, whether it's a roller coaster or whether it's a bucket of water. Okay, it ends up being the same problem then. M is 1.5 again. G is 9.81. Let's worry about positives and negatives now. Centripetal force. Hey, I'm at the bottom of the circle. Centripetal force, pos or neg? Got to act toward the center, right? If I'm at the bottom, the center is upwards, making it good. Positive value. What about gravity? Positive or negative? Hey, is it down or up? Olivia? It's downward, so we're going to make it a negative value, right? Normal force, I don't care, because I haven't plugged in numbers for the normal force yet. So I'll let the equation tell me whether it's positive or negative. Okay, let's do some math here. 3 squared is 9 times 1.5 divided by 0.75. Lightning fast calculation is 18. How do we get 18 for that? I told you there's always a trick, right? There's always a little cheat whenever we do something really quick in our heads like that. What's the cheat on this one? Boy, 1.5 times 3 squared divided by 0.75. Boy, that's not easy, is it? Yeah, 1.5 divided by 0.75 is 2. 2 times 9 is 18. So there's the cheat on that one. Makes it an easy question. Fn subtract 1.5 times 9.81 is 14 point. Somebody help me out on this one. 14.9715. Thank you. $14.9715? Oh, just 14.715. Thank you. All right, we're going to take that to the other side by adding, and therefore Fn becomes equal to 32.715 newtons. We're going to round that to 2 digits. We get 33 newtons. Hey, gravity was 14, or almost 15 newtons. The normal force is 33. We knew it had to be bigger, otherwise it wouldn't have stayed in the circle. The force toward the center must be bigger than the force that opposes it. Otherwise, it's not a centripetal force. Not a center-seeking force. Okay? Okay, let's take a look at two questions on page 264, please. We're going to skip question number 2. Here's the reason. Position B was right there. And that's what they're asking you to analyze in position B. Force of gravity is acting down. Which way is the normal force at position B? Toward the center, it's this way. Could you deal with that? Yeah, we could, right? We could deal with that using a two-dimensional vector analysis. But we don't need to in physics 20. Okay, that's beyond what we have to be able to do. So we won't. Okay? But in the end, if you ever see that sometime beyond physics 20, then deal with it the same way you deal with any other two-dimensional problem. We're not going to do that today. Today, I want you to focus on 1 and 3. 1 takes you back to that example you just did, and question 3 is a brand new question. Okay, let's see what we can do.